Hey folks, my name is Jerome Whittington, and today's talk is called Earthlight Displacements, the First Climate Model, and the Planetary Sensorium. I'm sitting here in my native environment among the humus and this scrappy tree, which seems to be having a bit of a love affair with this iron fence, partly because this is the kind of nature that really makes me happy, and partly because it's been so crazy warm this winter. But mostly I'm sitting out here because usually when we think of climate change, it's so insanely abstract. We understand climate change through all sorts of graphs and numbers, charts, like parts per million CO2 in the atmosphere. But too often we forget that climate change really has to do with very intimate and real things that are hard to think about because they're so fundamental, like what it means to live on a planet. When the sunlight enters the atmosphere, it's mostly visible light, the light our eyes can perceive, the light we earthlings have evolved to be able to sense. But then it hits this brown earth and it changes into infrared radiation, most of it, which we can feel by touch, but which is invisible. And here's the thing. Visible light can pass through the atmosphere really easily, but the same thing isn't true for infrared radiation. What we call a greenhouse gas is a gas like water vapor or CO2 that vibrates when it gets hit by certain wavelengths of light. How much does atmosphere block infrared radiation? That's the main thing I want to talk about today, because it was very much up for debate more than 120 years ago. In 1896, Svante Arhennius published a landmark paper in the Philosophical Transactions of the Royal Society of London, in which he described at length his effort to calculate the importance of atmospheric CO2 as a determinant of Earth's temperature. It was the world's first climate model. In his paper, he formulated the scientific question of climate change much in the way that it stands today, namely, what would be the effect of doubling atmospheric CO2 levels? He also articulated many of the main outlines of an answer that would continue to be affirmed more than a century later, and he grappled with the real problem of tabulating climatic variables at a global scale, that is, averages of data meant to represent the surface of the Earth. In this short video presentation, I want to link his quantitative effort to calculate a planetary scale phenomena with the empirical matter of sensing the Earth. If, as Paul Edwards has argued, climate science has elaborated a vast planetary-wide infrastructure that's radically changed our ability for measuring the atmosphere, then this is because climate politics is in some sense a politics of the sensible. Part 1, the first climate model. So what's up with Arrhenius, and why should anthropologists care? In the 1890s, Svante Arhennius was a big deal in Sweden, one of the country's most celebrated scientists. He received his doctorate in chemistry at Uppsala University in 1884 for research for which he would later receive a Nobel Prize. As far as the climate research goes, it has widely been heralded as an essential precursor to modern climate science, and partly that's true. He understood that there was a crucial feedback between CO2 levels and humidity, and that this feedback would drive temperature. He understood that industrial coal use could have an effect on climate, and he welcomed this because other evidence showed that the planet should be headed into a new ice age. While many of his ideas were visionary and speculative, his insistence on tedious quantification provided for both constraint and nuance in his most important scientific contributions. The organizing concern of debates about climate during his day had little to do with human effects on temperature, and much more to do with the emergence of deep time as a cultural and scientific problem. The repetitive nature of ice ages was the immediate empirical concern, and the temporal requirements of Darwinian evolution and also thermodynamics pointed toward both the immensity of deep geological time and to the essential contingency of human existence alone in the universe. His interest in atmosphere was deeply humanist. The quantitative effort was immense as well, and the publication itself is filled with page after page of tabulated data. Amazingly, to my mind anyway, Arrhenius' whole approach rested on the work of an American who had figured out how to measure the temperature of the moon. The planetary significance of his program thus resonated in more ways than one. It bears mentioning that the logic of quantification rests at the core of a materialist ontology of modern science, which above all holds that real things can be counted, preferably through a mechanical device that reduces the latitude of subjective perception. Feminist science studies scholars such as Michelle Murphy and Kath Weston, have argued that struggles over expertise have centered over control over the means of perception, the gynecological speculum and the handheld Geiger counter in the cases that they describe. But the additional issue here should return us to Donna Haraway's classic discussion of situated knowledge and the technological prosthesis. That is, measurement devices often perceive phenomena that are simply unavailable to quotidian embodied perception. The prosthesis establishes a kind of sensory alterity. This is certainly true of the device developed in the 1880s used to measure the moon's temperature. Part 2, Earthlight displacement. Arrhenius' model is full of nuance and sophistication, but for all that, it would have been fruitless were it not for the work of an American, Samuel Langley. Langley designed and built a device called a bolometer, which was capable of sensitive temperature measurements from great distances. In describing the bolometer, in 1880, Langley flagged both the historical contingency of science and the humanist problem of comprehending the planetary basis of life. He wrote, quote, "Very important new questions have arisen which science cannot answer, the most important of which concerns the heat of the solar spectrum. For this means a knowledge of the total energy by which we ourselves and all animated nature exist and act." Langley's language was heroic. He claimed the device was capable of measuring a temperature difference of 0.00001 degrees Celsius. It could detect the location of a cow from a mile's distance. For Arrhenius' purpose, Langley conducted a series of measurements of the temperature of the moon on clear nights as the moon ascended from an angle of 35 degrees above the horizon to its apex. As the moon gets higher in the sky, the heat rays have to pass through less and less atmosphere. From measuring the difference between these, he could calculate the ability of Earth's atmosphere to trap heat. Here I'll make my final point. That is, this measurement of moonlight was an Earthlight displacement. The question was, how much radiant heat did Earth's atmosphere absorb? For Earth's climate, the radiant heat in question is Earthlight, the glowing, mostly infrared radiation that escapes from Earth's surface. But there were no satellites to measure Earthlight from outside the atmosphere, no way to observe Earth from a distance necessary to gauge how much heat escaped the atmosphere back to space. So the moonlight was an essential substitute. It served as an approximation of this essential property of the atmosphere, its ability to trap heat and maintain the relative warmth of a planet capable of sustaining life. Thank you.